Bismillahirrahmanirrahim. Assalamu alaikum. Today we'll learn how we can model the footing in Plaxis software. So this is the lecture 1. So now what we will do in this tutorial, we'll find out the settlement of a circular footing. So we'll try to solve one example using Plaxis software. So let's understand what the problem is. So this is an example. So this is circular footing of diameter 2 meter, soil layer thickness is 4 meter, and these are the properties of sand. It's a homogeneous soil sand. Poisson's ratio is 0.3 and elasticity modulus is 13,000 kPa. So we'll try to model this into the Plaxis software. So before going to Plaxis, let me make you understand that there are two techniques to model the footings. So first technique is we predefine the displacement. Let's say we predefine the allowable settlement, that is 0.1 meter, and we want to find out that how much load will cause 0.1 meter displacement in the soil of this property. So the load that will cause 0.1 meter displacement depends on the properties of the soil. So if we are given these properties of the soil, then we will have to find out that how much load will be caused by this footing that will basically cause the displacement of 0.1 meter. Sometimes it is 25 mm allowable settlement. So we want to find out that how much load will cause the allowable settlement. So first technique is we can model prescribed displacement. We can define the prescribed displacement, and in the result we find out the load. The second technique is we define the load of footing, and we in result try to find out that how much settlement will be caused by the load of the footing. So these are the two techniques. We'll learn the first technique in this video lecture. So let's go to the Plaxis software. So how we can model in the Plaxis software. So while we open the Plaxis software, this dialog box will open. If we are to work on the new project, then we'll click on the new project and click OK. After clicking OK, this dialog box will appear. Now we'll have to provide the project details. So let's firstly write the name or title of the project, that is sand circular footing on sand soil. Okay. So no, this is very important. What is plane strain model and what is axis metric model? So to know what basically these models are, these are the definition of plane strain model. If the cross section of the geometry is uniform, like square footing or rectangular footing, then we'll use the plane strain model. From this definition it is clear that axis metric model is used when the cross section is of circular. Means for circular structures we'll use the axis metric model, that the loading scheme around the central axis will remain same on both the radial direction. What does it mean? If this is the circular footing axis symmetry, the loading scheme in both the radial direction, in these two directions, will be the same. So what does it mean? We can divide the whole geometry in two halves. We'll work on first one half. The same properties will be applied or projected to the other side. So we'll consider the one axis. This is called the axis metric case. So this is the case of plane strain model. So we have circular footing. Now we'll click over here the axis symmetry model. Now what is elements? 15 noded element and 6 noded element. So let's discuss this as well. What does it mean by the 6 noded and 15 noded element? This is the soil element. If we define one element divide into further 6 nodes, then it is called the 6 noded element. What does it mean? we want to find out the stresses and displacement etc at 6 points of this element. If we further subdivide the element into 15 points, then it will increase the accuracy, that we are able to find out the results at this point, at this point, at this point. So it is recommended to use 15 noded element. So we'll click the 15 noded element here. Now what is gravity angle is minus sign in Plaxis shows the downward direction. So 90 is at 90-degree, gravity is acting downward direction. X is acceleration, y axis acceleration are related to the dynamic analysis. When we are dealing with the dynamic analysis, then we have to consider these points. Now go to the dimension. This is length in meters, you can change kilonewton and day. Now this geometry dimension will have to be carefully adopted. When you will work on these, you will get to know how much important these dimensions are. So let's say in our case it's a 4 meter thickness. So if we define our scale 25 meter up and 50 meter in horizontal scale, so our model will be very small, the simulation will be small. So that's why if it is 4 meter, we cut it into half from here like this, and this will be 5 meter and this will be 1 meter radius. So what we will do, this will change it into 5 instead of 50, 5 meter. So spacing, grid spacing should be 0.5 or 0.25. We'll take it as 0.5. It is very important as well. If you have 0.5 spacing, then it means you can click the point or select the point of 2.5, 3.5 meters, 4.5 meter. If you select it 1 meter, then you will be only able to select 1 meter, 2 meter, 3 meter. So the points in between these you will not be able to select. If you have the dimensions in 11.25 meter, then you have to define the grid spacing into 0.25 meter and so on. So this is the concept of this spacing. So just click over here. Now after clicking this, it is pre-selected, line is pre-selected. Now in this direction we have to draw 5 meter from here. Click over here, go 5 meter, see in the horizontal direction above, this is 5 meter. Go in vertical axis in a 4 meter soil layer thickness. So you can see here 4, you can see here 5. So just click over here, 4, yes. Now move towards this, click over here, right click. So now you have defined the geometry. The next step is to provide the confinement. Why we provide the confinement, let's discuss. From here, standard fixed-is. If you click here, you will see such types of line. These two parallel lines represent the roller sport. Roller sport means the translation is allowed in only one direction. So in this case, displacement is allowed in vertical direction only. So this fixed-is show the fixed support. It means no area below this is influenced. So it is the fixed support to represent the bedrock or something like that. So the next step is to define the properties of this material. Go to this material set. Now here you can see plates, geogrades and anchors. These will be used when you have to model the structural elements, which we will learn in the upcoming video lectures. So in the meantime, we'll select the soil and interface. Group name order is none. Firstly, we want none. Now go to the new, and here give the name sand. And now by default model selected is Mohr column. Usually we in soil deal with the Mohr column model, but for special cases, soft soil, hardening soil, we can use these models. The detail of these models will be provided in the next video lectures. So because it is not possible to explain each and everything in one tutorial, so we'll discuss these models in the upcoming videos with their application as well, when we can use these models and what are the application of these models. So in the meantime, we'll use the 4-column model. Sand is a drain material. We'll select the drain. If we are dealing with the clay soil with very low permeability and loading rate is high, then it means there is undrained condition. We'll select undrained in case of clay soil, non-porous in case of concrete or something like that. So for the meantime, we'll select drain material. Now gamma unsaturated and gamma saturated, we are given these properties in this table. Gamma unsaturated is 17, gamma saturated is 20, permeability in x direction is 1, y direction is 1 meter per day. So we'll select this 17, this is 20, no, this is 1. Now parameters, we'll have to provide the elasticity, that is 13,000. Poisson's ratio is 0.3, we already know that. So 0.3 is Poisson's ratio. Now effective cohesion, and let's check. Cohesion is 1, friction angle is 31, dilatancy angle is 0. So dilatancy angle is provided in case of sand if the frictional angle is greater than 31. So dilatancy angle is considered when the sand is in loose state and volume changes are high. It means that sand particles will try to dilate, then we have to consider this angle as well. So usually when the angle of internal friction of sand is more than 31, then it is provided. We'll do an example regarding dilatancy angle in the next video. So in the meanwhile, we'll put these values. This is 1 as it is a cohesionless material. Sand 5 is 31, this is 0. Rest of the parameters are related to the dynamic analysis: shear wave velocity, primary wave velocity, and shear modulus, and elasticity. So next is the interface. Now we are considering the rigid case. In the rigid case, it means that there is no strength reduction in the soil due to the simulation of any element. Let's say if we model the structural element with the soil, then if the foundation is, we consider the flexible, then we'll select the manual. Then we have to find out the strength reduction factor. Let's say if we define diaphragm wall, then the soil that is interface with the diaphragm wall with the soil, then there will be strength reduction in the soil strength. So in that case, we have to provide that R interface, strength reduction due to interface. So now we'll change the color. Let's say we select this color. Okay. Now the sand material has been defined. Now we have to assign this property. Drag this to here. Now you can see the properties have been assigned. Okay. Now in the next step, we have to define the prescribed displacement. You can see it, prescribed displacement. Now in where we'll have to define, as we have cut this model into two halves due to axisymmetry. So from here the footing will be modeled from here to here, and will prescribe the displacement of 0.1 meter in this example. So I have selected this. Now from this to, you can see here, from this to this 1 meter due to the radius. Click over here and right click. You can see the prescribed displacement has been defined. What does it mean? When the displacement will be 1 meter, 0.1 meter, that how much load on this soil will cause 0.1 meter displacement. So that is what we have to find. In the meantime, we don't define the displacement. We'll define the displacement in the next stages. Now go to the generate mesh. Mesh has been generated like this. This is the 15 noded element, triangular. Okay, update. Now go to the initial condition. We have to define the initial condition. This dialog box will appear. Water weight is 10. We'll keep it as 10. Now the sand is dry, and you can see here phatic surface is by default at the datum. That it means now there is no water table effect over there. If we want to define the water table over here, then we'll have to define the water table from phatic surface from here. In the meantime, it's a dry sand, so we'll keep it as it is. We'll do the case that will deal the phatic surface or groundwater table in between the soil in the next video lectures. In the meantime, these are the two points where you will have to define the initial stresses. So we'll click the right button here. Now just click over here, these cross, generate initial stresses. We want to generate the initial stresses, so this dialog box will appear. This is based on Jackie's model. Jackie's model is 1 minus sine phi. 1 minus sine phi is 31, 1 minus sine 31, so this will appear k naught. K naught value 0.485. What does it mean? Sigma m weight. Summation m weight means the whole soil mass is included or will be affected if the value is 1. If there is a layered system, then we have to change this value. So in the meantime, we'll keep it as 1. The concept of this one is the whole soil mass is influenced by the loading. So okay, now update. Now we'll go to the calculate, and yes, circular sand save. Now the next phase of calculation will start. Click OK. Now you can change the name of the phase. There will be only one phase, so go. No, it's a plastic analysis. We'll deal with the other analysis, consolidation analysis, phi reduction, and dynamic analysis in the coming videos. In the meantime, it's a plastic analysis because there is loading on the sand, and on unloading there will be no elastic. It will be elastic to some extent. So go to the parameters, keep it, these things remain. 250 steps, it will take 250 steps to perform the calculation. These things will be discussed in the upcoming video lectures. Stage construction means a step-by-step process. So this will be discussed in the submerged excavation video, in the third or second video tutorial. Now we have to define. We'll define this thing that how much displacement is. Just click over here, double click. You know, by default it is -1. Minus sign shows downward direction, so we'll put the value -0.1 over here. -0.1 meter displacement is the predefined. So okay, it has been defined. Just update. Okay, before running the calculation, just select the points for curve. This is important because if you want to generate the curve of stress strain at the end, let's say I select this point where I want the stress and strain graph in the end. Just update. Now go to the calculation. The calculation will start, and you can see here it has started to calculate the force that is causing the displacement that we have defined. -0.1 meter, minus sign mean downward direction. Here you can see the force in negative. That has okay. Now prescribed ultimate state has been fully reached. It's okay. Now go to the multipliers and check the reached value. By clicking over here, you can see the force minus sign downward 177.38. That has to be multiplied by the 2 pi because it is kilonewton per radian. So if we multiply it by 2 pi due to the axis symmetry, we'll obtain the force in kilonewton. Let's say this is I'll open the paint software just to make you understand that how we can find out the force. Paint, So that is basically 2 pi into 177.3, so that comes out to be 1110 kilonewton, because 177 is basically kilonewton per radian force. So this is the force that has caused 0.1 meter vertical displacement in the sandy soil of properties that we have provided. So that is how we can find out the force by prescribed displacement analysis. Now we'll go to the output to check the further information. Now you can check the stresses, Cartesian effective stresses, deformation mesh, total displacement, and each and everything, vertical displacement. You can go to the contour shapes and then the shadings. You can check the values over here. This is, you can say, defined shape, let's say deformed mesh. This is 0.1 meter displacement and it will be deformed like this. Now the important step is to calculate, go to the curves program. I'll go to the curves program and now new chart. Okay, now I'll have to select that file I am working on. So circular footing on sand. By double clicking, this dialog box will open. Now I want a graph displacement along the x-axis and force along the y-axis. So just click over here. This is the point that I selected points for curve. If I select 2 points, then there will appear 2 points. In the meantime, I selected 1 point. These are the displacement vectors. I'll click y. If I select invert, then it will be invert direction. Okay, now you can see here the force is in this direction and the displacement 0.1 meter. Against this, if you want to check, this is 177 kilonewton per radian. You can see here per radian. If we have to multiply it by 2 pi, then the force will be in kilonewton. So if you place the cursor over here, you can see the Fy force minus 177 kilonewton per radian. If I want to format this curve, go to the format, curve, okay, regenerate, just invert it. Okay, then you can see the usual graph. Okay, this is, you can say, 200 kilonewton per radian, but the force is 177. So this is how we can perform the prescribed displacement analysis on Plaxis. I hope you liked the video. If you have liked, please subscribe the channel so that you may get the upcoming video lectures. Thank you. Allah Hafiz.